بسم الله الحمد لله رب العالمين والصلاة والسلام على أشرف الأنبياء. Shall I close the lights or So my thesis topic is about multi-path exploitation through the wall radar imaging using sparsity-driven detection, as you can see. So in this presentation, I will first introduce the topic, motivate it, and talk about what people have done before. I will also talk about some technical background, where we will have the mathematical models and more information, deep information about this topic. And then we will go to the first part of our thesis, which is about evaluating computer sensing algorithms and through-the-wall radar imaging via F1 score, and we will talk about more details, the evaluation methods, and the criteria that we use. Then we will go to the second topic that we have worked on, which is joint wall position detection and multi-path exploitation in through-the-wall radar imaging. And then we will conclude with some summary and future research. So now, we asked why through-the-wall radar imaging. But first, from its name, it is clear that we would like to see through the walls. We would like to see what are the things behind the walls. This will be good in several applications. For example, it will be good in surveillance and investigation. For example, here you can see there are some hostages, and the police would like to see who is inside this building. Another thing is it can be used in rescue missions. Let's say that there's a building on fire, and we would like to see are there people inside or not. It can be also be used in other applications as well. As any other topic, there should be, or there are challenges. I will talk about only 3 of these challenges through the wall radar imaging, but there are others, but I will talk about these 3 because they are related to my topic. At first, through the wall radar imaging, we demand high resolution images. We want high resolution in our image. To have this high resolution, we need to transmit a signal with wide bandwidth, and we need to have large aperture for the radar. So this means that we will have more data to collect, process, and store. So in 2010, Wang and his colleagues introduced compressive sensing through-the-wall radar imaging. Compressive sensing will help in solving this challenge. And then this one, at first, how Wang and his colleagues did it for step frequency radar, and then Zhang and Amin introduced it to impulse radar, which we will use inshallah. Another challenge is the multipath. For example, let's say that this is the scene that we want to image. So this is the transmitter, and this is the receiver. When we transmit when the signal propagates through the wall, it will reflect from the target and return back to the receiver. But the problem is that there will be other reflections coming from the target to the wall and back to the receiver. So this will cause what we call multipath ghosts. So in 2011. Somebody said, well, why not use this multipath? Why not use it to improve the signal, to improve our signal? So multipath exploitation was introduced in 2011 by Settler and Amin Morris also. Then in 2013, what they did is that also Liang or Lenzberg Michael with also Amin Morris, they introduced multipath exploitation under the framework of compressive sensing. So they solved 2 problems, the problem of multipath and the problem of data. And the third challenge in through-the-wall radar imaging is that we would like to discriminate desirable targets from those that we don't desire. Let's say that we want only moving targets. So the electromagnetic waves will reflect from the front wall, from other stationary targets or objects like the chairs, the walls, and we want to detect the moving objects. One way to solve this problem is to use what is called change detection. But what we do is that we take the image from several frames or several time samples and subtract them from each other so that the stationary returns will be cancelled. So in 2013, Ahmed Fawziya and Amin is also introduced change detection under the framework of compressive sensing. As you can see, you can note that Amin Munis, you said his name more than once. He contributed a lot in this topic, and he was one of the graduate students here in KFUPM. On the site. So these are the three challenges: data, multi-path returns, and detecting moving targets. For us, our objectives is to first compare the compressive sensing algorithms that are used. Compressive sensing algorithms are proliferating in literature. So we would like to see which are the best that we can apply to through the wall radar imaging. So that's the first objective. The second objective is we would like to join. We would like to exploit multi-path returns that are coming from moving targets under the framework of compressive sensing. So we will join. We will be working in this intersection between these three topics. So let's go more deeply to our contributions. At first, to be able to compare the algorithms, we have introduced the F1 score in evaluating the performance of compressive sensing algorithms. We used F1 score because it's a quantitative measure and it allows us to detect, to see how reliable the algorithm is in detection. The second contribution is that we have evaluated the performance of 14 compressive sensing algorithms when applied through the wall radar imaging. We have considered several SNR levels and compression rates, also several targets. The third contribution is that we introduced a general framework for joint wall position detection and multipath ghost suppression. We call this framework really wall pursuit. Under this framework, this framework allows for a family of algorithms to be inside this framework. We have proposed two of these algorithms, and we call them basic wall pursuit and dynamic wall pursuit algorithm. So now we will go to the technical. We will go deep in the technical background. We will talk about the signal and the scene model, and then we will talk about the three problems or the three main topics in our research. So let's say that here we have the transmitter, the target, and the receiver. So at first, the transmitter will send an ultra-wideband signal, which has a wide bandwidth and there's a narrow time domain. So that and then the receiver will receive this signal with a specific delay and some error over here, and some noise. Okay, so usually the ultra-wideband signals that we will use are less than 1 nanosecond. This will give us a high resolution. For example, if we have a pulse duration of 0.79 seconds, we will have a resolution of 5.7 centimeters. So this is for the signal. We would like to, and since we are sampling, we will not have it in time domain, or we will not have it continuous, so we need to sample it, right? So we will put things in vectors. So also the scene itself, we will divide it into many pixels, and then each pixel will represent one of the elements in the scene. So our received signal, the y, will be a vector, a column vector. It will equal psi mn. I will talk about this. X, which is the scene itself. So what we did is that we took each row or each row here and put them, concatenate them all into one tall vector, so that we have a vector plus this noise. So psi is what psi is that for each pixel we would like to see what is the received signal that we will have if there were a target over here. So if there were a target in this pixel, we would receive this signal over here, the gray one. And we will do the same thing for all of the pixels here. Okay? So this is psi. X will be the coefficient, the reflection coefficient of each pixel. So if there is no, so if we don't have a target, like this case, the first case, it will be 0. If we have a target as here, we will have some value that is related to its reflectivity. So for example 1.5, and the same here. All of them will be 0 except two non-zeros. So as you can see, this signal will be full of zeros, and it will have few non-zeros. We call this type of signals as sparse signals. Actually here, we will not have only one transmitter and one receiver. We will have multiple transmitters and multiple receivers. So how to deal with this? What we will do is that we'll take the received signal coming from each receiver and concatenate them all into one vector. The same thing for the matrices. We'll put them all into one vector matrix. So we will have this bigger vector, which is y equals psi x, where psi is this and y is this concatenated vector. So as you can see, we have lots of radar, lots of antennas, or a high aperture, so to have a high resolution. We will have a huge amount of data. So to solve this, we have compressive sensing, as we said. What is compressive sensing? Compressive sensing, and you can say that it's like what we want to do. We want to acquire and recover a sparse signal in the most efficient way. So we have this. So this is the y that we were just talking about. So what we will do, we will multiply it with a fat matrix where this will be compressed. And then, so while we are not receiving all of the measurements. We are only receiving some of the measurements, few measurements, and then we will reconstruct the signal, this sparse signal, by doing this optimization over here, that is written over here. So we will minimize it over we will minimize the first norm of the signal to get a sparse matrix or a sparse vector. So that's for the first, I think the compressive sensing part, the change detection part, to be able to sense the moving targets. So let's say that we have here two different frames. So in this frame, this target over here is stationary; it's not moving. However, the second target is moving, as you can see. So in change detection, what it says is that we'll do something simple. We'll just subtract the received signal that's coming from from the two different frames. So this is y L plus 1, where L stands for the frame number, and here this is y1. So this is the first frame, this is the frame L plus 1. So what we will do is that we will subtract these two signals from each other, and then what will happen is that we subtract these two received signals. That means that we will subtract this image from this image, right? Or this vector from this vector. That means that this target will be suppressed. So that's what we want. We want to suppress stationary targets. So in delta x here, we have three possible values. Either sigma p, which is the reflectivity of the target, if there were a target here. 0 if there was no target, and negative if there was a target here and not here. So now to the multipath side of the problem, we'll talk about the multipath model. So here, let's first see what's happening here. So we are transmitting a signal. It will reflect from the target. However, there will be other reflections, as you can see, coming from the other walls. So when we receive the signal, we will not receive, as we said before, that only psi and x. No, we will receive the direct path, and we will receive the one coming from the second path, the third path, and the fourth path. And all of these we can formulate them the same way that we formulated the previous the direct path problems. So let's say that for the first column here, in psi, it will have the expected signal, received signal if we have a target here, and it reflects from one of the walls. So since this can be formulated into a long matrix or a path matrix, multiplied by one tall or one long vector. To make things easy, we call all of these psi tilde and x tilde. As you can see, there's a W here, right? Because these are reflecting from the walls, this means that they are wall dependent, right? So this wall, the geometry of this room is different. What we will receive is different, right? So the multipath, so these dictionaries are affected by the wall positions. So this W, W1 until WR, they will give us information about the position or the place of the wall, of each wall. So here, for example, let's say there's one wall direction. So we can have many directions, R direction. So this is one wall direction. So we are discretizing this direction of the walls, and only one of them will be non-zero, which corresponds to the true position of the target. So now, if we know, let's say that we know the position of the walls, so we can get this vector, right? We can get this matrix, right? So if we have this matrix, we can apply this optimization method to construct the signal itself, the signal that we want. So now let's go to so since we have covered the background now, let's go to the first part of my thesis, which is evaluating the compression sensing algorithms in impulse through the wall radar imaging. So now, first we should ask, why do you want to evaluate these compression sensing algorithms? Use any one. Well, that's the problem. We would like to know which one is better to use, because it will affect our results at the end, right? So we should know which algorithm to use. Also, we would like to go towards an algorithm that's specifically for through the wall radar imaging. So before that, we would like to see what's in the literature, to know which methods are better than others. So these algorithms have been implemented through the wall radar imaging. Some of them are not algorithms specifically, some of them are optimization tools, but these are what we found in the literature. While looking at the algorithms, the different algorithms, we found that there are some features that specify a good algorithm. These features are that differ between from algorithm to another algorithm is the accuracy of reconstruction, also the processing time that it takes. Some of them take longer than others. The memory used, some of them use larger memory, and some of them are not immune to noise. Most of them are not immune to noise, but some of them are more immune than others. And the last thing is that some of them don't have practical parameters, such as knowing the number of non-zeros in the vector itself. So what we did is that we searched for the most popular algorithms in compression sensing, and we searched for those which have been implemented in radar, in the radar applications. So we found these 14 various algorithms. So we would like to evaluate. So if you want to ask what would we like to evaluate, we would like to evaluate the detection capabilities of these algorithms. How good will they detect the target? Will they give any? Will we have any missing targets? Will we have any false alarms or not? So we have tried some of the measures or some of the measures that are in literature, as target to color ratio, image SNR, peak side log ratio, mean square error. We tried all of these, but none of them gave us what we want. None of them gives us information about how well does this algorithm detect the targets or not. So this motivated us to go dig deep and see what are the things that are used to detect in detection, to see if we are detecting good or not. So here comes the F1 score, where let's say that in the actual scene we either have a target or not, right? So these two cases, And when we want to reconstruct the image, it's either that we say that there's a target here, or there's no target. So this is the thing that we predict. So what we predict is the same as what's real in life. That's good. That means we have correct target detection, and we call this true positive. If we fail to detect a target, we'll call this is called the missing target, and we also call it false negative. However, if there is no target, and we see that there is a target there, that means that we have introduced a false alarm, and we call this false positives. So these two are important, which give us insight about the target that we have missed, or the false alarms or the false targets that have arrived. So there are some measures. There's a measure called precision and recall, where we will take the ratio between the true positive and all of the things that we said we detected, all the targets that we detected. And the recall is the ratio between the true positives, what we have detected correctly, and the true targets that are there in the scene itself. So these are two different measures, the precision and the recall. If both of them, if one of them is large, if both of them are large, that will be great. That means that our system is good in detecting the targets. If one of them is larger than the other, that means that there's a problem, right? It's either that there are missed targets there. Even if we have a high recall, one of them will make a problem, right? So that's why we take the harmonic mean, which is the multiplication over the summation. Both of them are, if any one of them is low, the result of the harmonic mean will be low. So that's what we want. That's what we want. If one of them is low, we want something low. So this is called the F1 score. This is called the F1 score. It has been introduced in, I think, the 60s in information retrieval. So let's say that this is the vector that we have reconstructed from the compressive sensing algorithm. What we will do is that since the compressive sensing algorithm will give us continuous values, it will not give us either a 0 or 1, we will threshold it several times and see which threshold will give us the maximum F1 score and take that as the performance measure. So let's go to what we have simulated. These are the information about the simulations that we have did. We have a region of interest of 4 meters by 4 meters. This is the thickness of the wall, the dielectric constant. We have 3 transmitters and 1 receiver. The image resolution is 5 centimeters. We have a target size of 25 centimeters by 25. We have sent a 0.71 Gaussian pulse. And what we did is that we limited the work of each algorithm to only work at 0.2 seconds to have a fair comparison. Because some of them will take a long time, take maybe 5, 10 minutes, 20 minutes, and some of them will take less time. So to fix this variable, we fixed all of them to work on only 0.2 seconds, and we did this over, and the results that we will show are over 100 runs. So we want to test 3 main things. We want to see how the SNR, the signal to noise ratio, will affect the detection of the algorithm. We want to see how the amount of data used, the compressed data will affect, and the number of targets, how will they affect the algorithm. So for the SNR, we used these SNRs from -15 until 40 SNR. For the amount of data, we used all of the data, 50%, 50%, until 5% of the data. For the number of targets, we tried 1 target, 4 targets, until 13 targets to see how they will affect. And so we got many results, but I will only show the extreme results, the extreme ones, so that they have a taste of what's happening. So let's start with the SNR. We want to see the effect of the SNR, signal to noise ratio. So in this case, we have no data reduction. We are using all of the data, all of the data. So, and we have only 4 targets. So as you can see, that from 0 dB until 30 dB, the algorithms are giving us similar performance. However, when we go to lower SNR ratio, SNR values, you can see that they vary. The performance varies from algorithm to another. The best that we can see for this case is what is called the YAL1 algorithm. And the worst one is the L1LS algorithm. So the other algorithms have similar moderate performance here, as you can see. So this is with using no reduction.